Boleh?
Boleh, Doktor.
Okay, Assalamualaikum warahmatullahi and good afternoon for all. So for today, going to continue what we left last week. Remaining the asymptotic analysis, the asymptotic analysis. Before we continue the second lectures, the third week lectures, to the fundamental of analysis. Okay, before that, go back to this. What is asymptotic analysis, so that we can get the against the background of asymptotic analysis. So, what is asymptotic analysis? Is estimating the running time of an algorithm. we may end up the asymptotic behavior as the growth of f of n, as n get large. For example, when we have a function f n equal to c times m squared times k. For example, okay, look, for example, these are the functions. When n get large, our main concern is the behavior of n. When n get large until certain infinity, for example. Let's say we have this c times n squared times k for some constant factors c and k. Let's say when we do the analysis, end up with this. We have some constants and we have the n. So our main concern is n basically, because we want to estimate the running time, the behavior or the asymptotic behavior when we increase the n until certain numbers, until infinity, for example. So asymptotic analysis is said this algorithm to be symptotically equivalent to n squared, as n get infinity. Get large until the infinity. So we can conclude that's n squared only, because even though we have the some constant here, but constant we increase the n, it will remain constants. So basically, in general, it won't affect that the behavior of the when n grows. So our main constant is n. So that's why we can conclude that is n squared only. We can conclude without, considering the constant. When we include the constant, basically, every time it's just a constant. Okay. So it is not important to know the constant factors, because they wouldn't affect the upper bound or the lower bound or the type bound of running time. So for example, we have 3. These are some constant c times n squared plus another constant k. For example, 100 here. So the main constant actually, our main constant is n squared only. Okay. This can be further discussed when we reach to the discussion on the for each synthetic analysis called the big O, big omega, big theta. Okay. So order of growth, most important, order of growth within constant multiple as n get infinity here. Example, how much faster will I going to run on computer? That is twice as fast. How much longer does it take to solve problem of double input size? This is actually the issues of when we increase the n until certain numbers as infinity. So as it grows, so we need to estimate the patterns or the behavior of the n when the input size grows. Okay. These are basic asymptotic analysis, efficiency class, as we discussed last week. You still remember, we have a constant 1 logarithm log n, linear n, and we have a function called n log n, or n time log n, simply n log n, and followed by quadratic function and square, and after that we have a cubic and cubes, and this n quadratic or cubic basically is a polynomial grow, and where we have a exponential grow, in the form of 2 to the power of n, and base 2 doesn't matter, can be any base, and factorial is n factorial. These are the basics, what we call efficiency class, from lowest, which is constant or 1, to the highest, which is n factorial. So we can see that the difference when we increase that the n input size. So when we do the analysis, it will fall under maybe under log ones, maybe n and log n, so on and so forth. It depends on the certain algorithm. Okay, and this is the what we have described or explained before. The details of each synthetic efficiency class started with O1. So we denote as T of M. T actually indicate that the time, running time of N. So we want to see that the running time when N increases until infinity. So what is the big O? So here is, if the big O is O1, main big O1, this is called constant growth, mean the running time T of N when increases to the certain numbers, certain limit until infinity, does not grow at all as a function of n. It is a constant. So this is actually the first FC class. Actually, when we increase the input size of n until certain number, for this algorithm, we say it won't increase at all the time, at all the running time. So this called the constant. So there's no real example, real algorithm for this, except only we can, we can see that array access. Mean you want to retrieve the values inside the array by pointing to the certain index number. Let's say I equal to whatever, maybe n here, whatever size here, maybe 10, then automatically you can retrieve the value for that, the tens index, or maybe thousands, or maybe millions. So basically, with the same time taken, if we, let's say for the n I equal to 10, we retrieve maybe 1 millisecond. And similarly with the others, like n I equal to millions, we can simply retrieve with the same time. So this is actually the FC class O1, meaning that when you increase the number of n, the input size, it won't increase at all the time. It becomes constant. When we plot the diagram, the graph basically becomes straight line. Okay. The second followed by, the FC class log n. O log n, B O of log n, the running time. This called the logarithmic growth. T of n grows as the base 2 logarithm of n. Actually, the base doesn't matter. It is just traditional to use base 2 in computer science. Can be base 10 and whatever, because that one is I think it doesn't matter. What we need is actually the pattern log function here. So for example, binary search has this characteristics. That's why when we do the analysis for binary search, the big O is O log n. Big O of log n. So this is actually the big O for this binary search. So this is the second MC class, and third is ON. This called linear growth. T of n grows linearly with n. For example, looping over all the element in one dimensional array would be 1. A good example for this is sequential search, where we want to find the search key inside the list, the array. Start with 0 until n minus 1. We have to go through every of the index, everyone. 0, 1, 2 until the n minus 1. So we have to go through one by one. This become basically efficiency class is ON, because we have to go through for each of the element inside the list. And finally, not finally. The fourth efficiency class is n time log n, or simply n log n. This is called n log n grows. T of n grow as n time the base 2 logarithm of n. For example, heap sort and merge sort had this characteristic. So we can see that n log n basically is higher, slightly higher than n. I mean, after the n, we have n time log n. This is actually the functions based on the synthetic efficiency class. And next is O, big O of n to power of k, where k basically greater than 1. Can be n to power of 2, 3, 4, until what that this called a polynomial growth. Polynomial growth, t of n grow as the k power of n. The example of this selection sort is an example of polynomial growth rate. It is n o n squared, big O n squared. Mean the higher, higher, a bit higher than the n time log n. And next is big O n to power of 2 power of n. This called the exponential growth. T of n grow exponentially. It is pronounced big O of 2 to the n. So exponential growth is the most feared growth pattern in computer science. Algorithm that grow this way are basically useless for anything, but only for when you apply for the very small problem only, or very small instance. So in computer science, we traditionally use the constant 2, but any other positive constant could be used to express the same idea. So we use the constant 2 power n, maybe 3, 4, doesn't matter, the same thing. So you want to see that to classify that there's this pattern basically under this what we call that exponential growth. Okay. Next is this the last under the class, the highest class called n factorial, big of n factorial. This called factorial growth. T of n growth factorially. It is also the most feared growth pattern in computer science. Okay, so we have all this from the lowest, which is O1, until the highest, which is n factorial. I do hope that you understand this. This is the benchmark, what we call the efficiency class or order of growth, when we do the analysis to know that or to estimate the complexity of the algorithm in terms of time complexity. Okay, we have others complexity under the space efficiency, but here is actually for the time, because the space complexity of space efficiency is nowadays is not the big issue, because we have enough memory size nowadays. Okay. This is the values when we substitute the values. For example, you can see the difference. This is the input size n. When we increase the input size from 10 uh, to 10 power 1 until the 10 power 6, which is 1 million here. If log n for the n, so we have this log 10 is 3.3, and n is a 10, 10, 10, and n time log n 3.3 times 10, so on and so forth. This is the pattern. So we can see it will increase here. When we increase the here, when increase the n here, it will increase also the time here. Okay, that's called the running time, T of n here. Want to estimate the time, the running time of n when n increases until certain point, which is until the infinity, our limit. Okay, these are the graph that shows us the difference from the graphical perspective. When we have the O1, basically the strength, these are actually the x-axis is the n. When n until the increase until the infinity start with greater than 1, is input 1 until whatever n until the infinity. And this y-axis is actually the time, running time, where basically when increases, it will increase the t, the running time here. So we plot the diagram here. You can see if fall under the O1, the straight line here, log n is actually slightly higher than O1, but in between the On. And we have others is n log n, n time log n squared, n cubed, and finally this is actually the n factorial, the highest, the highest efficiency class. Okay, so when we have this case study, for example, we have 60 times n squared. There's some constant c, and we have another constant here, c. This c1, c2, and c3. For example, this some we have 3 constant here, and we have 2 n here, n squared, and n here. So basically, when we have like this, so we take the highest here. So we can conclude that this n squared only in conclusion, right? So these are the highest. So our main concern basically, the n. When n increases, we don't take care much on the constant, because constant basically when we increase that the n here, it won't increase at all. 60 uh 60 when we increase the n, still 60, 5 still 5, 1 still 1. That's why we can just, I mean, ignore the constant into actually for the analysis in order to estimate and conclude the BO. So our main concern is actually the n here, when n squared or n here. Okay. So when we are taking this example, actually when we start to here, we the first column here, we are taking into the considerations all the constant, three constant here, plus the variable here, the n. So when we substitute the value, when we start with 10, for example, we increase by uh, 100, 1,000 and 10,000 here. We can see the value here, 6,051. It will increase like this. But when we are taking only one constant here, 60 times n squared. So the value 600, 6,000, 60,000, and until the 6 million here. But only when we take only the n only and ignore all the constants, three constant. So basically the value is less, but the pattern basically the same, will increase like this. Increase like this, the same patterns. Okay. So when we plot the diagram here, for here, basically we look like the same, but when we increase the values and take consideration this, all the constant, so the patterns basically like this. When we consider only one constant, 60 times n squared, the pattern basically similarly the same. When we only take the n only, n squared, the pattern basically the same. So we can conclude that in order to estimate the running time for the BO, we can only take that the n increases, mean n input size, and we can omit or ignore all the constant. Even the constant, basically, maybe we can see that the constant will affect, but not what I call that, mean affect that the whole of the analysis of the running time. Okay. Okay. Any questions so far? Ada soalan? Clear so far the basic of the asymptotic efficiency class, from lowest to the highest, from the O1 to the n squared. N factorial. Clear?
Right now clear.
Okay. And now we're going to discuss a bit further on the asymptotic notation so that we can understand the what we call before this. Someone asked me about the upper bound. Like now we have upper bound, lower bound, and tight bound. Upper bound basically relate to the big O. Lower bound big omega, and theta is a tight bound. So we're going to discuss a bit further so that you can understand that what is actually the synthetic notations and also the big O, big omega, big theta. Okay, and finally we'll discuss on the theory, on the graph, the upper bound, lower bound, and tight bound. Okay, there are two functions denoted as t. T, as I mentioned just now, is denote as the running time. T of n is a function to estimate the n. N is we want to see the patterns, the behavior when n increases until certain point, which is infinity, the highest, the limit. And we have another function g of n, where g actually these two functions we want to discuss here. So can be any non-negative function defined on the set of natural numbers. Okay. T of n will be an algorithm running time, as I mentioned just now, usually indicated by its basic operation. So count as C of n. So in general term is T of n, which is running time, but we can go further to estimate in detail by using the C here, as C of n, which is C sometimes as a comparison. We want to compare, especially like the searching is about comparison. We compare search key K and compare throughout all the index inside the list or the array. So that's called the basic operation. We denote as a C because the comparison. When n here, n increases. And we have another function, g of n will be some simple function to compare the count with including some multiple constant. So we have g of n actually C time g of n here, where we consider this as a constant, which is the upper bound, and we want to estimate our f of n is the behavior of n when increases without the constant factors. Okay, to compare and rank such order of growth, computer science use the three notation: big O, big omega, and big theta. Okay, how these terms comes in. To as a order of growth, our computer science in order to estimate or to benchmark the complexity of the algorithm based on these three notation: big O, big omega, and big theta. Okay, look at this. This is a big theory, but you have to get that the conclusion for this. What we call the upper bound. Big O actually tell us about the upper bound. What is the upper bound? So we have the function g of m, big O of g of n equal to a function of n. There exists positive constant c and not such that fn here. So this c actually that represent the constant c times g of n. So we want to increase n increases here. We have this function where when the function here like this, right? And want to estimate the of m here, the function n when n increases here from certain point here and not here. And not is actually start with n uh, equal to greater than 0 or n greater than equal to 1. Start with 1 here. Because when you do the function here, it will start here and finally some point here it will become stable and finally you want to estimate this function. Okay, this is the behavior of the n when n increases. Okay, and we have the mfn here. The function is must be greater than equal to 0 and must be less than equal to c g of n, because c g of n is actually the upper bound. When we consider that all the constant, basically this is the upper bound. Okay, we want to estimate the n here for the big O perspective from the big O perspective. Basically, we want to estimate the growth here, the n growth until the upper bound here, and it won't exceed that this upper bound with the constant. That is the conclusion for this graph. And the big O notation define n upper bound of n algorithm in bound a function only from the above. Mean from the above, from the here, Cj n here. From here. So from here to this. From upper to lower. So whatever here and here we get, for example, the upper here, maybe these are the n squared here. Okay. So actually from n squared to the lower here. Okay. For example, insertion sort. Worst case scenario, n squared. Let's say when we do the analysis, when n increases for the insertion sort, you end up with n squared. So n squared is actually the upper bound. When we consider also the constant here, they become the upper bound. So the lower bound maybe the lower function maybe O n, like this n here. So we have the O n squared. The lower one based on expression is we have n log n, right? We have n, we have log n until the O1. So these are the function that actually lower than n squared. The n squared here is actually the upper bound. So when we conclude for the instance sort, the BO is m squared, meaning that regardless the numbers of n when n increases until whatever numbers until infinity, the highest or could be only n squared, can be only n squared. You cannot exceed than that. That is called this the upper bound. Okay. Essentially, notation for BO example. For example, O of g of n is the set of all functions with a lower of same order of growth as gn to within a constant multiple as n goes to infinity. For example, here n. So we have the n element of big O of n squared. So meaning that this is the n squared is actually the upper bound. When we have the n actually is element of n squared. And we have the some constant 100 times n plus 5 element of n squared, meaning that when we do the analysis, we can conclude this n. So even though we have the constant here, but n element of n squared here. See, this is actually the upper bound here, and the actually the function that below than the n squared actually is element of n squared. And the third is half of n, half n times n minus 1 here, also the element of n squared. So this tells us that this is the upper bound uh, from the perspective of big O. Okay, any question? Ada soalan yang ni? Boleh faham tak? The theory here. Ada soalan?
Tak ada, Doktor.
Tak ada, boleh faham? Boleh ya? So the big O is the upper bound. So we can conclude that the big O is the upper bound, and the G C times G of n is a function where we consider all the constants. Okay, and when we try to estimate the function of certain algorithm, that when n increases, so the highest is actually the upper bound. When you do the analysis, finally maybe end up with n squared, then at the n squared is the upper bound. So maybe when we reduce that n, so the n maybe become from the n squared, maybe the lowest is maybe n times log n, or maybe log n and maybe O1. That is actually the meaning of the big O, the upper bound. Okay. Next is the big omega. What is the big omega? Big omega is actually the lower bound, means starting from the lower to the above. So we have the omega of g of n, where we want to estimate the n, the function here. When n increases, there is this positive constant c, similar what we discussed just now, the upper bound, which is the big O, and n not such that c times g of n greater than equal to 0 and less than equal to fn here for all n when n greater than equal to n naught here. So what does it mean here? We have this starting the function here from n naught here, here to this when increase. So this is function that the behavior that we want to estimate when n increases, and this is actually the lower bound, the big omega, where we consider the constant c time of gm. So meaning that this is the lower bound. Okay. And the big omega notation define a lower bound of an algorithm is bound a function only from the below, instead of from the above, the the upper, like the big O just now. Okay. So in short, the best case is theta n. So the omega n is the least use of notation. So meaning that if we have this, we look at this the example here. Okay, let's say we have this theta of g of n stand for the set of all function with a highest of same order of growth as gn to within a constant multiple as n goes into infinity. For example, we have this n cube here is element of theta omega of n squared. Correct? Because these are the highest, because this is actually the lower bound. And also this half n times n is end up with n squared. Also element of n here, because the lower bound here, these are equal. And but 100 times n plus 5, not element of omega n squared. Why here? Why this not element squared? Someone can someone maybe have a respond for this?
Because it only n, not n squared.
Because this only n, because the lower bound is n squared. So this actually the normal n squared. the n is here, right? Here, n. So not element of n squared. Okay. But here, if based on the, let's say we have the 100n plus 5 is element of O n squared, right? Correct. This correct, right? Because when we indicate that big O is actually the upper bound. The upper bound, and this is actually the lower. And here, this is the lower. This is actually the lower bound, but this is actually the lower from this n squared. So this is not element of this theta omega. Okay, clear? Any question? Boleh faham? Ada soalan? Tak ada?
Tak ada, Sir.
Okay. Next is a big theta. Big theta is the type bound. Type bound basically in between the upper bound and the lower bound. So based on the theory here, theta of g of n, where we have want to estimate the function of n when n increases, there exists positive constant c1, c2, and n not such that c1 times g of n greater than equal to 0 and less than equal to a function of n when we want to estimate the n increases here, and must be less than equal to c2 times g of n for all. When you look at this is c2, which is the upper bound. This is actually the lower bound. So now n increases here, want to estimate is actually in between here. This is the type bound, the theta. Okay, the big theta notation define bound a function from above and below, so it defines exact symptomatic behavior. Okay, so this is actually the conclusion when if we want to estimate based on the function the big theta, basically want to estimate in between the average of the running time, whether it is in between the upper bound or lower bound. This is the same thing. There's no example for this. So as a conclusion, asymmetric order of growth, a way of comparing function that ignores constant factor and small input size. So if big O of g of n, class of function f n that grows no faster than gn, mean no faster than gn, the n here, okay? For the theta here, class of function f n that grow at same rate as gm, in between. For the omega, class of function of n, f of n that grows at least as fast as gn. So this is conclusion can be made from the graph just now. Okay. Any questions so far? No question.
No questions, sir.
Okay. Establishing order of growth using the definition, actually as a recap, f of n is in O of g of n if order of growth of f of n means less than or equal to order of growth of gn within constant multiple. For example, there is positive constant c and non-negative integer, and not such that here. This is the same will include that f of n. And here when we try to estimate the n here for certain algorithm must be less than c times g of n for every n greater than n not here. Example here, we have 10 n times n is actually O n squared, mean element of n squared. When we have 5 times n plus 20 is also O n, is equal. Just now we have a less than or equal. This is less than, this are the equal, less than, this equal basically. Okay. Okay, best case, average case, worst case. For some algorithms, depend on form of input. We have the worst case. Worst case is maximum over input of n size. This actually what we try to through the big O is actually the highest, the upper bound, basically the worst case. The best case is minimum over input of size n, maybe the lower bound. Average case is average over input of size n, number of time the basic operation will be executed on typical input. Not the average from worst case basic, meaning that we cannot just get the worst case plus the best case and get the average divide by 2, because the average case basically based on the probability. Okay, expected number of basic operation considered as a random variable under some assumption about the probability distribution of all possible input. So the average case basically based on the probability, not simply we get the worst case plus best case and divide by 2. That is not the average case. Okay, we need to use the probability in order to get the average case. Okay, I give the simple example sequences. This sequences basically we can see that I less than n, when n ai not equal to k, it will repeat until what? So we have the array here. The array start 0 until n minus 1. So we need to have the k here. We need to check at start with 0, element 0, index 0, 1 until the n minus 1, one by one. This become on. So basically the worst case for the sequences is on. So that is the upper bound. So let's say if n we have 1 million, so we have to go through 1 million index. If we have 10 million index, we have to go through until the n, whatever n, until infinity. That is the worst case. Okay. So if best case, which is the best case based on this? Okay. The best case is when we found that the search key at index 0. When we try to compare k here, whether it is in the index, located in the index, let's say 0. When we search into this index 0, we found the key, automatically we terminate, because based on this, when AI not equal to k, when AI index 0 equal to k, it will terminate the loop. Then we found already the search key. That is the best case. That is the best case. Okay, it won't go through all until the end because we have this condition. The average case is if the best case is index 0, the worst case is index m minus 1. Okay, this is a worst case. This is the best case. Meaning that in between here, in the 1 until n minus 2 here, that is the average case in general. We can conclude like that. So this is actually a good example to understand that what is the worst case, best case, and the average case. Okay, any soalan? Ada soalan? Clear? So far?
Yeah.
Okay. Empirical analysis. Okay, we finished the theoretical analysis. Before this, in order to, to measure the complexity or the time you see for certain algorithm, we have two ways. The first is theoretical analysis. The theoretical analysis is mathematical analysis, also the synthetic analysis in particular, right? The second is based on empirical analysis. The empirical analysis, actually, we have to conduct experiment. So, like this, we have to select a specific typical sample of input. Mean we need to have the input size, we increase maybe by 10, 20 and so on. Use physical unit of time, so we have to record the time, maybe millisecond. Count actual number of basic operation. The basic operation is the C of n, whatever. If we have the comparison, how many comparison we have to count, we have to calculate, and we have to total up the basic operation. And after that, analyze the empirical data. Means when we have we write a program, for example, we increase the input size. For each, we have to record the time. After we record time, we plot a diagram like this. For example, this is a bar diagram, or maybe a time diagram, it depends. So after that, we can see that if the pattern like this, we short the pattern like this, then we can conclude that this maybe is linear. In terms of time, linear. The algorithm is linear, quite efficient. If the pattern maybe become like this, maybe this is factorial. Okay, so we can see that based on the diagram here, visualization. So we cannot have like what we had just now. The order of growth are O1, O, log N, O, N, because there's no such thing for the machine dependent numerical analysis. We can only look at that the pattern of the graph. From there, we can conclude whether it is efficient or not. Okay. Okay, we finish what we week 2. Continue from the last week lecture. Any question before we move on to the week 3? Ada soalan? Clear?
Yeah.
Okay.
Yes, sir.
Yeah, okay. Okay, this is week 3. For this week, basically, our lectures on the analysis of iterative algorithm. As I mentioned earlier, we have two type of algorithm in terms of implementation of the algorithm. Number one, it iterative or non-recursive, where we can use normal iterative through the loop, like for loop, do while loop, and while loop. Or we have another implementation algorithm is recursive. Recursive is using certain method, and after that we call it back, and become the repetition, also the loop, that is recursion. So this iterative or non-recursive algorithm. So we start with the iterative algorithm or non-recursive algorithm for analysis. How we going to do the analysis for iterative algorithm or for the non-recursive algorithm. And later, next week, I will introduce for recursive algorithm, because these two implementation requires different method in order to do analysis for each. Okay. Okay. Before we do the analysis, this is actually the important thing you need to know: the input size and running time, and how to count the input size and running time. What is the input size? The input size is basically based on the n. When n increases, what we talked about just now. When n increases, that becomes the input size, meaning we increase the input, the n, and after that, what is the running time? So where we have to observe that the running time, the time increase according to the input size increases. Okay. Okay, let us assume that counting the following a simple algorithm instruction. Let's say we have very simple algorithm. We have the M here, the variable here. We have the array here, A0, where basically we assign the, okay, where we assign here the whatever value inside the array 0, index 0 to the M here, which is the variable here. This is called the assignment statement from right to the left. Okay, we have the loop here, the repetition using the for, because this is actually for the iterative. We have I equal to 0. This initializer start with the 0, and this is a condition when I less than n. When it is true, it will execute whatever inside the block here, where A are inside assigned to the M. And after that, you increase by 1 by 1. 1 is I equal to 0, plus 1, 1, plus 1, 2, 3, until the N. Okay, this is actually the simple instruction or simple algorithm that we're going to discuss, and as an example on how to count the input size and running time after this. Okay. Looking up the values of a particular element in an array, this is how basically we have to, based on this, after that, assign a value to a variable, where we assign whatever value from right to the left, and comparing to variable I less than whatever here, n, until the m, incrementing values I equal to I plus 1 until the end. These are repetition, the process, assigning a values to m until the m here. This is actually to describe the algorithm above. Okay. And if you want to count it, to calculate, to get that to estimate the running time here. So maybe it become like this. Here m equal to A0, mean that we want to assign the index here. First, we need to retrieve this. This become one operation. And then when assigned to m, become another operation. This is called the basic operation. And for I equal to 0, so we have one basic operation. And I less than n, meaning that this become repeat until the n time. This n time, also the increment also n time. And here also n time when this condition is true, right? So ai into n time. So basically, you want to calculate exactly line by line, become like this, okay? The number of instructions for this algorithm needed is 3, 1, 2, 3 plus n, 3n here. 3 plus 3n. This is how we can calculate exactly, basically. So we can define a mathematical function of f of n 3 plus 3n here. And finally, it end up with f of n plus 3 plus 3n. But the question is, do we really need to count for every instruction or operation? If we have a complex algorithm, I think it is difficult to calculate everything. So the answer will be no. We only need to find the basic operation, the most important operation of the algorithm. So the question is, what is the basic operation? Okay, next. Okay, theoretical analysis of time scene. Now we're talking about the theoretical analysis, the empirical analysis or the experiment based on the theory, based on the mathematical analysis. In particular, based on asymptotic analysis as we discussed just now. Okay, time machine is analyzed by determining the numbers of repetition of the basic operation as a function of input size. So the keyword here is basic operation. What is the basic operation? Okay, so basic operation, the operation that contribute most toward the running time of the algorithm. We need to find what is the operation. Assignment is one operation. The repetition loop I less than n is also the basic operation. But we need to find that operation, the basic operation, the operation that contribute most toward the running time of the algorithm. Mean the operation that that affect that the whole running time of the algorithm. Okay, look at this. We have the input size. Based on this, this is actually the function that we're going to uh, observe. We have the t of n is a running time when n increases, and approximate is c of the operation c of n. So this actually this t is a running time, and c here is the number of time basic operation is executed. We want to find that this. And C op here is the equation of time for basic operation. This is the formula. And typically, types of formula for basic operations count like this. Sometimes we have, when we do the analysis, end up with, we get the exact formula. Or maybe sometimes we get that formula indicating order growth with specific multiplicative constant with some constant like this. 0.5 times n with some constant. Or maybe we have this in the form of formula indicating order of growth with unknown multiplicative constant like this, with some unknown constant, c times n squared. Okay, these are actually the type of formula for basic operation count. After we do the analysis, we will end up maybe exact formula, maybe formula with some constant, maybe formula with some unknown multiplicative constant. Okay. Okay, what is the input size? So input size and basic operation example. So let's say we have the problem here. Just as some example, searching for key in the list of an item. This is actually for the searching problem. And the input size measure is number of list item. For example, n. So we have an n size, that is actually the input size. If n equal 10, we have 10 element of array, that is the input size. If we describe that, we give that the n mean the value of n 1 million, become 1 million. So the basic operation here is key comparison. What does it mean? So under the searching, we have the key. We want to find that key whether exists in the element on the array until whatever size, input size is n. N is the number of array size, the size of the array. So we want to compare. Start with index 0, followed by 1, 2 until the m minus 1. That is the key comparison. The basic operation is comparison. That's why we denote as C of n. C of n here, where we have the general function Tm. We want to estimate the time and equal to C of n. C of n is actually denote as the specific basic operation. Sometimes maybe we denote as A. A is addition, A of n. Maybe some denote as M, M of n. Depend on the problem, depend on the basic operation. So go back to this, which one? I think the previous slide. Okay, the previous slide. And the second example is multiplication of two matrices. We have matrix A and B. For example, we want to multiply A and B, the product of A and B. So that called the multiplication of two matrices. What is the input size? So metric dimensions or total number of them. If m times n times n is actually the size, input the size. If m times n, that is actually the input size. So basic operation is multiplication of m. So for this, we denote as here is m of n. We use the m. That is the basic operation. Okay. And third example, checking primality of given integer. And primality is prime is a prime like the prime number here. Want to check whether it is a primes number or not in a given integer n. So the input size is n size, number of digit in binary representation, where we have to put that digit, and finally we need to represent the binary representation, and the basic operation is division. Okay. And finally, the last example, typical graph problem. So when the graph, basically the input size is different based on, because the graph we have the vertices and edges. So the input size is we need to know how many vertices and how many edges. That will be the input size measurement. And the basic process is visiting a vertex or traversing an edges. So that called the traversal. How many traversal mean from one point, one node to other node? So we need to traverse. That is actually the basic operation if we consider as a graph problem. Okay, clear the basic operation? Any question? Ada soalan?
Clear, Doctor.
Clear. Okay. Okay. Next, iterative versus recursive algorithm. As I mentioned earlier, we have two implementation of the algorithm, whether iterative or also called non-recursive, and we have another called recursive algorithm. What is the difference? Okay, so iteration or non-recursion and recursion are key computer science technique used in creating algorithm and developing software. These are the standard where we have the main in order to do the repetition. So we can have a repetition, whether it become using the normal repetition like using the for loop or while loop or do while loop in the programming perspective, or we can do also repetition by using the recursive method, where we have the method, the function, and finally we call the same function, and finally we reduce at a certain stopping criteria, what we call the base criteria, and that is also a repetition. So this is called the repetition. So an iterative function is one that loop to repeat some part of the code, and a recursive function is one that call itself again to repeat the code. This is what I described just now, the difference between the iterative or non-recursive versus recursive algorithm. So iteration and recursion are probably best explained using an example of something that can be done using either technique. Maybe you can look at this. This is factorial, right? Factorial. You know what about factorial? Let's say we have factorial 5. 5 factorial. What is the answer? 5 factorial, what is the answer?
25.
25? Not 25. Any other answer? 5 factorial?
120.
Yes, how you get this? I will get the 103. So it is like this, right? Factorial 5 times 4 times 3 times 2 times 1. What is the answer?
120.
120. This is a 5 factorial. Okay. This is actually the repetitive, right? So this factorial can be solved or can be written by whether using iterative or recursive. If the iterative like this, why using the while here? So while factorial value here greater than equal to 1. If this, we give the initial value of fact value is 1 because factorial 1 factorial is equal to 1. So that's why we give the value 1 here, the default value. But while factorial greater than 1, mean 2 above, then we need to do this. Factorial values, fact values time n here. Time n. Okay. What is the n? If n equal to 5 here, so here, just now you want 1 time 5. And after that, 3, 4, and so on and so forth. And we need to reduce it, n minus minus, so that it will reduce like this. 5, if n equals 5, and 5 minus 1, 4, 3, 2, 1. This is the pattern. We want to calculate and finally get the result of 120. And after return the values of factorial here, fact value here on this. These are iterative style, iterative methods. Okay, approach. For the recursive approach, like this, we have the method here called we declare the method factorial here with the n here, integer n, and finally we have here the same method, but we need to look, decrease by 1, n minus 1, so that we can 5, 4, 3, 2, 1. We will stop 1. When n equal to 0, we return 1 because factorial is 1. So when this is stopping 5 until the 0 here. When n equals 0, it will return 1 automatically. As so n time factorial n minus 1. So this actually we reduce from the 5 here, and this 4, and finally 3, 2, and this is the repetition basically become like this. And finally we stop here. Stop at n equal to 0. Okay, clear?
Yeah, doctor.
Clear. Can you see the difference between the iterative style approach versus the recursive approach? So all about the repetition, loop. But loop can be done by two ways here. Whether either using the iterative, using in the programming perspective, we have the for loop, while loop, and do while loop. Or also you can implement it using the recursive, where we have the method, and after that we have to call itself. And call itself mean with the same function here, but you have to reduce the parameter n here, so that it become n equal to 0, whatever base criteria you will stop. This how we're going to stop for the recursive, basically based on the base criteria. These are the base criteria here for factor here, which is n equal to 0 here. This base criteria. When you satisfied this the n equal to 0, it automatically will stop and return the values. Okay. So any other questions? Tak ada. No question, eh?
Tak ada.
Okay. Recursion. It is a problem-solving process. In general, a process is a process where it does or call the same process itself. In particular, a method call or invoke itself. So it call a method call or invoke itself. Break a problem into identical problem but getting smaller problem. You can see that from n minus 1. So from 5 factorial, 4 factorial, 3 factorial, 2 factorial, 1 until the 0. That is how it break down into smaller problem, and finally it will stop and it will get the solution, solve the problem accordingly. Okay, recursion. Recursive algorithm that find the solution has one to a given problem. Oh, I think this okay, recursion is algorithm that find the solutions and stop here. Okay, has one to a given problem by reducing the problem to smaller version of itself or more base cases. So implemented using recursive method that called itself. And recursion basically we have the base case in recursive division in which the solution is obtained directly. The base case actually the stopping point where during the iteration it will stop based on the base case and stop the recursions. Okay, we finish the difference between iterative and recursion. Okay, now before we go to the analysis the iterative, we need to review back our some actually mathematical aspect, a useful formula for the analysis. So basically, in order to do the analysis, you need to know a bit on the logarithm. So you have to back to school, also the commensal and the summation formula. These three mathematical aspect you need to understand because you need to apply during the analysis. Okay, for example, the logarithm, the properties of log here, all log bases are assumed to be greater than 1. In the formula below, log x denote the logarithm base 2, lons x denote to logarithm natural log based on the area here 2.7, and x are obviously a positive numbers. So for example, we have a log 1 base a equal to 0, or log a base a equal to 1. These are the basic properties of log. You have to remember back. And we have the log x power of 2 y base a, similar to the equal to y time log x base a, and logs x time y base a equal to this log x base a plus log y base a, and we have log x y. So we have the log x base a minus log y base a, and also we have this a for log x base b equal to x log a base b, and so on and so forth. This you have to since you have already the note, please look at this log property, because during the analysis we may use this as our basics foundation to do the analysis. And the commensal, we have three things for the commensal. We have combination, permutation, and subset. Okay. So number of combinatoric number of permutation of n element is set p of n and n factorial. Okay. And number of k combination of an element set c n of k, where we have n choose k. So basically we have n factorial divide by k factorial times m minus k factorial. This is how actually we can get that the number of combinations. And number of subset is basically 2 to power of n here. Okay, that's why from here we can see that when involve combinatorial problem, so basically the algorithm is very complex. It end up with n factorial, could be. Also you end up with this exponential 2 to power of n. So this, whether factorial or exponential grow, as we discussed before this, become the most pure algorithm, which is useless for anything, but only for the small instant. We can use for small instant. If we try to use for the bigger input size, become becomes too complex. I mean, in terms of time, sometimes we cannot solve the problem within the certain time frame. Maybe more than years, or maybe 100 years to complete the process. So the permutation, the different from the permutation and combination. Permutation when the order doesn't matter. The order doesn't matter. Combination when the order does matter. The permutation when the order does matter. Combination when the order doesn't matter. Let's say we have A, B here, C. So maybe we choose 2 from there. Maybe we can have A, B, or we have B, A. We have A, C. We have C, A. So we have B, C. We have C, B. Right? So permutation when the order does matter, mean the order is a matter. So basically these are permutation. AB and BA basically not is not equal to BA. For the combination basically when AB is equal to BA, mean the order doesn't matter. AB and BA basically the same, but permutation AB BA basically is not the same. That is the difference between the permutation and combination. Okay, this is a summation formula. We have 8 summation. This basically later on when we do the analysis, we have to refer to this summation formula. And we have one, basically if this formula, when increased by 1, 1 by 1 by 1, plus 1 plus 1. So basically this end up with n. So finally, when the pattern like this, we can conclude as ON. Okay, ON. Here, the pattern like this, when the repetition, where I equal to 1 until the end, I, mean I, the pattern is I, 1 plus 2 plus 3 until the end. So and finally end up with this equal to here, half n squared here. So basically we can conclude as n squared, BON squared here for the analysis. When the pattern like this, I equal to 1 until the end, but the pattern I squared here, 1 squared, 2 squared until the n squared here, and finally this become n cubed, and so on and so forth. So you have to look at this so that later on we can use this as our basis, to, I mean, to estimate the time, running time when we try to do the big O later on. Okay, okay. Okay, these are some of the still under the summation, some multiplication rules. Like this, you have to review. If we have the summation here, I equal to L until mu here, C times AI equal to this. When we have the C here, time the summation AI here, or maybe we have the plus minus here, equal to this. When we simplify, become like this. And similar with this 3 and 4 here. So you can check this in order to prove that the big O later on. Okay, I give the example. I think a bit. Maybe we continue during the lab. Boleh tak yang ni sebab nak kena ni mungkin dalam lab besok untuk grup C dan juga untuk grup Cik Aziz saya dah beritahu. Yang ni nanti mungkin dalam lab akan di explain in the details. Okay, how to do analysis paralysis? For example, we have the constant B of O1 here. O1, we have the N here. As I mentioned earlier, in our order of growth, we have this the first class, the starting, the lowest. But in a real case, real algorithm, basically no such thing, no such algorithm fall under this. A good example only when we try to access the array, the value inside the array, retrieve. So when the n equal to tens, basically we want to increase the value inside this. So basically requires the same. When increase the 10, also the 10 squared, 10 cube. So we can retrieve automatically direct to that particular index, whether let's say n equal to 10, automatically in that tens, or maybe in that hundreds, 1,000 million, we can retrieve that. So this is the first FC class. Clear? Any question? Tak ada.
Tak ada.
Tak ada.
Okay. The second is log n. So this example, basically, when we have this algorithm, artificial algorithm here, for example, this is a looping algorithm, I equal to 1, I less than n, I equal to I times 2. And automatically, for this given already, the big O here is O log n. Okay, all n. It's given already. Even any existing eigenvalue basic given already the big O. But now, how going to prove that is O log n? Where is how we going to calculate? And finally we get this log n. That is the question now. Okay. So basically, the first step, number one, there's no standard method to get that big O. So what you need to do is you have to trace it. Trace and observe the pattern. How to trace? So you have to trace. If I equal to 1 and I less than n. Let's say n is equal to 8 here. Okay, 8. So this true, right? So we have the I equal to 1, and finally I 1 less than 8, true. And now I update I time 2. You see 1 times 2 is 2. 2. Now I equal to 2. 2 less than 8, true. And 2 times 2, 4. Now 1, 2, 4, and finally 4 times 8, 8. Right. So this is a pattern. 8 times 2, 16. So you need to observe the pattern here. How to observe the pattern? Okay, I think we skip this. We go to the next first. These are quite simple. Let's say we observe this. I equal to 1. Let's say we have the 8. Yeah, the same thing. So I equal to 8, 1, and third increase by 1, 2, increase by 1, increase 1, right? So become 1, 2, 3, 4, until the 8. Then we stop. So this actually increase by 1 by 1. Increase 1 by 1. 1. So we can write 1 plus 1 plus 1 until the end. So this pattern, if we spot this pattern, basically we can check back to our here summation. What is the pattern here? Formula number
1.
1. So formula number 1 here, basically we can conclude that this ON, automatically we can conclude this as ON. ON. Correct?
Yes.
So if we apply the formula to prove that the formula just now, we have this mu minus L plus 1. So if we prove that, so we have the mu minus L plus 1. So mu is actually the n. The assumption like this, where n, and we have I equal to 1 and 1 by 1, right? So mu is n minus L is 1, because I equal to 1 here. 1 plus 1 here. 1 plus 1. And finally, we can simplify this 1 minus 1 plus 1 minus 1 plus 1. This actually remaining is n. So we can conclude is O n. Okay? Get it? Boleh dapat dah? Boleh?
Boleh, Doktor.
Okay. Now, back to this example. This number 2. I'll get this number 2 here. O n, log n. Okay. So look at this. The increase here, the pattern here, based on 1, 2, 4, 8. And this actually the n. But until what? Until 2 to power of k, right? Okay. If 1, 2 power of 0, what? 1. 2 power of 1, 1. 2 power of 2, 2. 2 power of 3, 8, right? So this is a pattern until 2 power of k. Okay. Can you see the pattern here? This is the increase of n. The n increase is not 1 by 1. Just now 1 by 1. But now 1 I times 2, the pattern we got like 1, 2, 4, 8, and it look like 2 power 0, 2 power 1, 2 power 3 until 2 power k. Correct? Is it correct?
Yes.
Okay. Okay, now for this basically is not n, it's not n, but is less than n. Must be less than n because it's n 1 plus 1 1. But here is the pattern like this. So the n here now is n here is 2 power of k. Correct? Is it correct? N now is the pattern is 2 power of k, not 1 plus 1. Is it correct?
Betul.
Okay, based on the order of growth, this is not n. End up with n or n. Must be less than n, correct? What is the class less than n? If the class less than n is log n, right? So we assume that this log n. So we may put this log n, and also we put the log 2 power of k here. Okay, let me